Swayam Prabha. Digital India. Educated India.
Welcome everyone to this NPTEL online certification course on techniques of materials characterization. So, we are on module 11 and we are discussing about X-ray diffraction. Until up to now in this module we have developed the relationship or the equation for calculating the structure factor, and we discussed about the importance of structure factor. Basically structure factor calculates, or structure factor relates the crystalline structure or crystal arrangement, atomic arrangement in a crystalline material to the X-ray diffraction that we finally receive, the intensity of X-ray diffraction finally we receive. And we see that a structure factor is basically very important, because even if the Bragg's condition is satisfied for certain planes, due to the structure factor or due to the restrictions imposed by structure factor, we do not get certain atomic planes. Even though the Bragg's condition is satisfied for them, certain planes we do not get any kind of intensity. So, this we have derived for until up to now. In the last class we derived it such relationship of structure factor for two crystal systems. One is the simple cubic and another one is a base centered. One is the simple crystal structure or simple orthogonal crystal structure, and one is the base centered orthogonal crystal structure. So, now in this week again we will be continuing this discussion and we will calculate the structure factor for two other general type of crystal structures. Body centered, one is body centered crystal structure, another one is the face centered crystal structure. And if time permits, we will try to do structure factor calculation for a more complex crystal structure, that is a NaCl crystal structure. So, let us start this our discussion on the structure factor calculation for a body centered crystal structure. So, here we have shown this is the BCC, body centered crystals. This is a body centered structure, not a body centered cubic structure as such. We are not it is a more of a generalized structure. So, we will possibly omit this last C and we will call it a body centered crystal structure as such. Okay. So, here as we can understand, it has two different two atomic positions. One set of atom is obviously at the corner position, and by now we know that this is one set of that atom. 0 0 0 is the position of that atom. And then another set of atom is this one, which is lying somewhere within the within this crystal structure, within this unit cell, and that is called the body centering position. And that position we can write it in terms of the fractional relationship. If you remember UVW, which was basically UVW, just for yourself I am writing it again, UVW, which is nothing but basically x by A, y by b and z by c, the fractional coordinates. So, in the same way now we are writing the fractional coordinates of that position as half of half. Okay. So, this is the body centering, the two atomic positions for a body centered unit cell, and this one half of half, this is called body centering translation. Body centering translation. This means basically that if you take a corner atom 0 0 0 and if you apply this translation over this 0 0 0 position corner atom, this atom, let us say if we apply this half of half translation, this atom will go. So, if we start with this one, we apply an half here and half in z direction, we arrive at this body centering position. So, half of half is basically called the body centering translation. Okay. So, now we know the structure factor, how it should be written. So, structure factor is basically where n equals 1 to capital N, f n e pi I into basically e 2 pi I into h u plus k w k v plus L w. So, this is the general formula for structure factor calculation. So, we are now applying this on a body centered crystal. So, what we can write the first one, and let us assume that this is composed of the same type of crystal. So, we can have the atomic scattering factor F to be here, and then we have for the first one, this one, we have E pi I, and by now you know that how it turns out to be, and this one comes out to be 0 of course, plus we have this E 2 pi I, and then we put this half of half. So, what we get h by 2 plus k by 2 plus L by 2. Okay. So, this is the structure factor, and then from here what we are getting F equals now 1 plus E pi I, okay, into h plus k plus L. Fine. Now, what we have to see, we have seen this for base centered also, how we determine the sign of this F just simply from various combination of this h plus k plus L, and we have derived some general formula. So, we have seen if this is an even integer of pi I, then this will come out to be 1. If it is an odd integer, then this will come out to be minus 1. Okay, this E pi I, if it is an even integer, so remember that E n pi I equals minus 1 is to the power n, that relationship. So, from there we know this has to be an even integer of pi I in order to make this one 1, and finally that will make it 2f. If it is odd integer, this one n is an odd integer here, this will become minus 1, and ultimately there will not be any intensity. So, we put that, now that becomes h plus k plus L. This has to be even, and if this is even, then F will be only F, okay, sorry, here it will be F, and then we are getting 1 plus this entire thing will come out to be another 1. So, we get 2f, and the intensity, we know the intensity is basically nothing but mod of f square. So, it comes out to be around 4 f square. This is what the final intensity we are getting if this h plus k plus L is even, and if h plus k plus L, this is odd, then what we are getting F equals F into 1 minus 1 now, and this turns out to be 0. So, that means if h plus k plus L is even, we are going to get an intensity which is equal to 4 f square. If h plus k plus L is odd, then we are not getting any intensity for that particular atomic plane, and this kind of planes which basically does not give us any intensity because of the structure factor restriction are called forbidden reflections. These are called forbidden reflections, means they are not possible, these reflections are not possible. So, what gives us this combination h plus k plus L equals even? For example, if we took something like 1 1 0, right, 1 plus 1 plus 0 is again an odd number. So, 1 plus 1 plus 0, this has come out to be an even number, this will be giving us an reflection. Second, the next one we can check out, this is something like 2 0 0, right. So, 2 0 0, again this is coming out to be even. The third one we can possibly write is something like we can think 2 2 0, okay. So, this will give us another reflection. What will not give, that means this condition odd, this will be let us say 1 0 0, this will be an odd, h plus k plus L is odd, this will not give us any kind of intensity for the diffracted beam. Then we can have 1 1 1 will not give anything. So, these are the forbidden reflections in case of a body centered crystal structure. So, let us see if this is true or not. So, this is now an X-ray diffraction from a BCC, body centered cubic. Now, we are dealing with a with a specific crystal structure, and this is a bulk metallic glass, equiatomic bulk metallic glass, or this you can see crystalline form of bulk metallic. This is basically a high entropy alloy, that's what you can call. Anyway, so if you see this has the BCC structure, of course, if you see the first reflection that we are getting here is basically 110, then 200, 211, again 211, if you take this H plus K plus L, 211 H plus K plus S is 4, so this is possible. Then the next one 202, 310 and so on. So what you can see here for this BC versus if you take something like SC, simple cubic. So BC, because of this restriction, if I take 100, 110, 111, 100 not possible, 110 yes, 111 not possible again. If I take simple cubic, then we already know that for simple cubic the structure factor is irrespective of HKL. Any combination will give you certain amount of intensity for this. So all of them I can have an intensity. So just if I look at the this diffraction pattern and I somehow get, basically I get the peaks for all of this 100, 110 and 111, I know it has to be, at least it is not body centered, definitely, because in body centered case I should not get 100 or 111, it has to be something like simple cubic. It is not, and if we can see the difference between, let's say again base centered and body centered, the one where we started, if you remember, then we were showing that 100 was, this was possible in case of base centered, but this was not possible in case of body centered. If you remember, we begin our discussion of diffracted intensity with this example, and now we can see the same thing. This is again, this is for base centered, where we are seeing that the 100 type intensity, this 100, basically a variation of 100. So this is possible here, but 020 there is nothing like a 020 in case of a BC. This is body centered. Okay. So in case of a body centered, we can again, if we look at this body centered versus base centered, then we can see that 100, 110, 111. So we do not get any 100, we only get 110 and 111, again we do not get it. In case of a base centered, if you remember, we are getting 100 because there the condition is H plus K, only H plus K has to be even. L is not valid here, L is not of any relevance in case of a base centered. So again 110, 111. So which one we are going to get here? This. So this is again, sorry, we will not get this one because here H plus K, we will get the second order one, we will not get this one. So 200 we will get, but not 100 of course. 110 again we will get it, this 110 definitely here, but 111 we will not get in case of base centered. What you are seeing here, that we are not getting anything from 111, we are getting the second order one, but we are definitely not getting the 111 peak for this one. So again, from this diffraction patterns we can make out some idea about the crystal structure just by looking at the which of these diffracted beams, which of these diffraction lines are possible in the dexter diffraction pattern. From there we can find out the crystal structure. So this is one way of solving the crystal structure. Okay. So now let us come to this face centered crystal structure. Okay. So face centered, again it is a crystal structure, face centering crystal structure, where you have 8 atoms in the corner. So those 8 atoms in the corner giving us 1 8 plus we have at face center position this and 2 of this. So we have 6 of these face centering positions, face centered atoms, but they are shared with 2 unit cells. So their contribution here is half. Altogether we have 1 plus 3, this many atoms, total 4 number of effective atoms in case of a face centered crystal structure. So of course this corner one will have 0 0 0, by now we all know this. Now what about the face centered ones? So face centered ones we can have like this, half half 0, then we have half 0 half, then we have 0 half half. So, these are the general fractional coordinates of the face centered atoms, three of these face centered atoms. This is the general fractional coordinate, and this one, just like body centered translation, this is called face centering translation. Face centering translation. Okay. So, that means if I start with a corner atom and I apply this, let us say half 0. So, I go half distance here and half distance in the y direction, no movement in the z direction, I will arrive to this face centered atom. So, same thing if I do in all different directions, I will be arriving to face centering atom starting from this corner atom. So, this is what the face centering translation means. Okay. So, in this case again structure factor will be, we start with the same kind of atom. So, atomic scattering factor is amplitude, and the first one of course E pi I into 0 plus the second one now E pi I into H plus K by 2, we can write like this, and what we can write for the other one E 2 pi I into K plus L by 2, and the last one will be E 2 pi I and L plus H by 2. Okay. Altogether it is giving us this F equals 1 plus E into pi I H plus K plus E pi I K plus L plus E pi I L plus H. Okay. Right. So, now what I understand, what we understand that this entire thing E pi I H plus K, E pi I K plus L and E pi I L plus H, this entire one, the H depending on the value of H, K and L, this entire sum, this 1 plus this entire sum, either it will be like 0 or it will be something like a 1 plus 1 plus 1 plus 1, something like that, or 1 plus some. So, some definite value other than non-zero value. So, this one can either have non-zero value or complete 0 value depending on this various combinations of H plus K plus H, K and L, not H plus K plus L, H, K and L. So, we will be now considering different combination of this H and H, K and L. So, first one we consider, then let us say H, K, L, they are unmixed. So, what does unmixed mean? Unmixed means either all are even or all are odd. So, H plus K plus L, either all of them are even or all of them are odd. Okay? In that condition, if we consider this unmixed, either all even or all odd, then what will happen? H plus K, K plus L and L plus H. In this condition, either all even or all odd, they all will turn out to be even. Okay? If H plus K plus L is unmixed, that means either all odd or all even, then this all of them will turn out to be even. And how it is done? Let us take a quick example that I am taking, okay, H, K, L all to be odd, 1, 1, 1. Fine, all of them are odd, 1, 1, 1. Then this H plus K will be 2, K plus L will be 2, L plus H will be 2, and all of them will be even, right. This is one condition. In that situation, F will be F and then this will be 1. Here this is even, so this will now be an even integer of pi I, so it will be 1. This will be an even integer of pi I 1, this will be an even integer of pi I 1. Ultimately, this will be 4f. So, that means I will get an intensity I equals again mod of f square, which is now 16f square. Okay. So, this is the intensity for this condition. Another condition can be HKL, where this is mixed, and mixed means, what does mixed means? They are like two of them, two conditions can happen of course, either two are odd, or sorry, 2 even plus 1 odd, or 1 odd plus, or 2 odd 1 even, sorry, 1 even. Let me just this, let me erase this part. Yes, 1 even and 2 odd. Okay. So, what will happen in this condition? H plus K, K plus L and L plus H, all of them will be odd, whatever you take it. So, if I take, let us say this example of this, if I take HKL, what can I take? 100 maybe, yeah, because 1 is 1 odd, 00 even. So, in this case H plus K, 1 and 0 1, K plus L, that is this 2, 0 and 0, this will be now again here. So, this will be an odd number, this will be an even number, but again this will be another odd number. So, in this case F will be something like F, atomic scattering factor, into 1. The first one H plus K, this is an odd number. So, this is giving me -1. K plus L, this is again an even number. So, this is going to give me a +1, and last one is again -1. So, altogether this will be 0. I will not get any intensity from an 100 plane in case of a face centered cubic crystal structure. So, this I asked you to try. So, this one I have tried with this combination 2 even 1 odd. You can also try it with combination like 1 even and 2 odds, then also it should give you, for example, 1 even 2 odd, I am giving you a clue, that will be something like 1 even 2 odd. So, this will be something like what it should be, 1 even is 0 and 2 odds will be, let us say 1 1. Okay. So, you can check out this also 0 1 1, another mixed one. So, what should be the intensity, and cross check this, verify this whether that will be 0 or not. So, but basically what you understand is that in case of an FCC or in case of a face centered crystal structure, you will be getting the first reflection from 1 1 1, not from 1 0 0 or 0 1 1, because both of them are mixed. So, this is the condition for an FCC. So, here it is shown for silver, this is an FCC face centered cubic crystal structure. The first one starts from 1 1 1. We do not get any intensity for something like 1 0 0 or 1 1 or 1 1 0 here. We straight away start with something like 1 1 1. Then we are, next one we are getting is 2 0 0, because again here it is unmixed, all of them are even, and then we are not getting anything from something like 2 1 1. 2 1 1 is a mixed, we are getting something 2 2 0. So, if we now we can compare this with some other crystal structures, for example, BCC and FCC. Now, if we compare this BCC and we compare FCC. So, what we are getting here is 1 0 0, 1 1 0, 1 1 1. So, we are not getting this, we are getting this, we are not getting this. So, in case of a BCC, for FCC, this, this and this, we are not getting this, we are not getting this, we are getting this. So, this is clearly a difference just by looking at this diffraction patterns, and if I can able to solve, I will be able to know a difference, and this is very very interesting, very important, where if we have something like a phase transformation, the best example of this possibly is something like gamma to alpha transformation. So, where For iron, in case of a iron, alpha, gamma to gamma phase to alpha phase, austenite to ferrite transformation. So, there what we have is high temperature, we have this gamma phase, or we have this FCC austenite phase changing to BCC ferrite phase, and there just by looking at this phase transformation, how the change is happening and how this peaks are changing. For FCC structure, we will be getting this 111 peak, and slowly as it transforms to BCC structure, we will see that 100 peak starts coming in, and then BCC structure again some other peaks, higher order peaks also will be coming in. One peak will diminish, another peak will coming out. So, this phase transformation, in case of a phase transformation, this kind of phase transformation, we can very well identify such phase transformation just from taking this X-ray diffraction patterns, different temperature, and we will be able to see how this transformation basically changes, which plane is giving rise to which plane, and lots of things can be done just by simply looking at these peaks or the change in the structure factor. Okay. So, structure factor, about couple of general things that we must remember about structure factor. So, first of all, structure factor, when we derive all of these structure factors, like for simple cubic, like for body centered, like for face centered cubic, what we mentioned is just like the general or the general structure of this unit cell. We didn't mention about the shape of the unit cells. For example, when we said simple cubic, we didn't, or simple structure, we didn't say simple cubic or so on. When we said base centered, we meant orthorhombic, but we didn't really entered those information like orthorhombic crystal structure A, B, C should be A not equal to B not equal to C, alpha, beta, gamma should be 90 degrees. So, those information didn't come in the face centered. If you remember the structure factor here again, if I write the structure factor again here. So, in the general form of the structure factor, this, if this is the general factor, we understand that this is the general expression for structure factor. This does not contain any crystallographic information. What does this mean? This means that this structure factor is independent of the shape and size of the unit cell. So, this does not depend on A, B, C or alpha, beta, gamma. This angles, the structure factor expression does not have anything like A, B, C or alpha, beta, gamma. So, that means the base centering can be anything as long as it is orthogonal. Of course, if it changes, this orthogonal gonality is changed, then the structure factor expression will definitely change. But as long as it is an orthonormal, that means alpha, beta, gamma equals 90. If we consider this, it does not depend on ABC, whether ABC is equal or not equal, it does not depend on that. That means the body centered cell will have any kind of body centered. If it is a body centered cell, any kind of body centered cell will have missing reflections from H plus K plus L. If H plus K plus L is an odd number, then that will not be coming in the X-ray diffraction pattern, whether the unit cell is cubic, tetragonal or orthorhombic. That is it. So, that is what. So, for example, what we mean here is that if I just think about 111 reflection. So, this 111 reflection will not be there whether it is a body centered cubic or body centered tetragonal or body centered orthorhombic. Whatever be the structure, just body centering, simple body centering will make this intensity, intensity from this crystallographic plane to disappear. It does not need to, or it will not be a special case for body centered cubic or body centered tetragonal or body centered orthorhombic. It will, for all cases, this will be not there. Similar thing for face centering, we have already seen that in case of a face centering, we did not have anything like something like 110. So, 110, whether it is face centered cubic or face centered tetragonal is not there, but any other face centering case does not matter, it will not be there. So, this is this relationship that we have derived here is very much general and it does not depend on the particular unit cell that we take. It it does not, it is so general. So, structure factor is independent of the shape and size of the unit cell. Okay. So, another thing that we need to discuss is that certain cells, if we go for a more complex crystal structure, then structure factor modifies even more. Other than this relationship that we already derived, other than this relationship, there has to be some more relationship, or there are more ways of modifying the intensity if some certain reflections are absent, which are possible with a simple calculation, structure factor calculation. Additional conditions are coming up, additional conditions are controlling the intensity of the diffracted beams in case of more complex crystal structure. This we will take some particular examples, for example like diamond cubic structure in case of silicon, and we will be also discussing possibly the structure factor of NaCl crystal structure in the next class. Sure.